Okay, so we're talking about capacitors, and we said 1 farad is a very large unit of measure. 1 farad can store 1 coulomb at 1 unit. How much is a coulomb again? 6.28 times 10 to the 18th power of electrons. All right. Make that I, so we'll make this one II. And we say often represented. Often represented. Because it's such a large number, we're probably mostly going to be working in PFs, which is what? Picofarads. Which is, how much is a 1 pico? 1 times 10 to the negative 12. All right, capacitance in a capacitor. C-A-P-A-C-I-T-A-N-C-E. Capacitance in a capacitor of a capacitor of a capacitor. Could I just abbreviate by cap? A-C-I-T-O-R. Depends on 3 things. What are those 3 things?
Frequency.
Crickets, crickets, crickets. Not yet. Area. That's good. That's coming. Area of the plates. The bigger the plates, the more electrons you can store. Right? That's why a big capacitors are sized the way they are. So I could write that. The bigger the plates, the more electrons can be stored.
That's only surface area.
Stored. What do you mean it's only surface areas?
That's only surface area.
As opposed to what? Thickness?
So only the side that's facing the other plate.
Yes. Wait a minute. Ask that again. Only the side that faces the other plate?
The other plate.
Yes, but they aren't necessarily just parallel plates. They can be rolled.
So the outside of it wouldn't be.
Depends on how it's rolled. Thickness of the dielectric. Thickness of the dielectric. What's the dielectric?
The thingy in the middle.
The thingy in the middle is correct. All right, the closer the plates are to each other, the closer the plates are to each other, the more electrons are attracted to the opposite plate. More electrons are attracted to the other plate. Which is to say, if the plates are far apart, the electrons aren't attracted to the other side. There's no attraction. But the closer you bring them, the more they're going to want to be attracted. Now, what happens if you get them too close?
Short.
Yeah, they jump across. And so that doesn't work out. So here's a rather large capacitor that's been cut apart. What is this right here? This tissue paper is what? Dielectric. And so what is this metal film right here? There's my plate. And you can see right there how it has a little foil going to each one of the plates in there. So if you need a tissue, you can take off a little bit of this, but all right. 3 things. I wonder what the third could be. The what?
Shout it out, bud. Scream it to the sky.
Frequency.
Not yet. Dielectric material. So, and the reason why it's not frequency yet is because we take a look at like this capacitor right here that says right on it 0.025 farads. Now, when they stamped that on there, did they know the frequency that was on there? No. So the amount of farads is not dependent upon frequency. It's a physical property. Just like the first few things we talked about how many henries in a coil was the physical property. How many winds it has, what's the core material. So the same as with this. So area of plates, thickness of the dielectric, and what is the dielectric material. So common material, air, glass, ceramic. There's paper right there. I have a bunch of notes here. Just trying to figure out how far I want to go with this. Air is the standard medium with the dielectric constant of 1. Not important. Dielectric strength is the ability of the dielectric to resist breakdown. Ooh, what is breakdown?
The ability to resist.
I mean, you hear it a lot. Rappers, break it down. And so, not rappers per se, but more like, where's the one guy?
MC Hammer.
MC Hammer, that's what I was thinking. Break it down. He was actually a little known fact. He's from the Bay Area, and he was a electrical engineer at first. So when he says break it down, he is in fact talking about. And he does have another song, something ode to Farad, but didn't make the top 10. Anyway, so what is breakdown?
How's that other song go?
What other song?
You just mentioned?
Well, I don't remember it.
No.
I remember a few lines, but it has some explicit things that I can't repeat.
You can
So.
pause it.
All right, so what is it? I can what?
You can pause that.
Okay. What is breakdown here? What do I mean by a breakdown?
When it becomes a conductor. Well, it becomes a conductor through the amount of current put into it.
Okay, I like that. It could actually become a conductor due to the amount of current. So you put enough current or voltage through anything, and it can become a conductor. It just fine. The air is a brilliant conductor when you have enough voltage. An example of that is lightning. So comes right through, right? Maybe saying it's a conductor isn't the best way to do it, but what happens if something breaks down? So, this is just tissue paper, and it's not conductive, but if you put enough voltage through from one plate to the other, it'll just arc across, and that's breakdown. So just arcing right through it. So breakdown, let me see what was I going to say about that. Breakdown, also known as leakage. So at some point, you're going to be testing capacitors, or a condenser is the better term at that point, of your magnetos, and you're going to be doing a leakage test, which is to see how much it is broken down. And you're going to find that it does have a certain amount of leakage. And that's where the insulation is broken down, and you're allowed a certain amount of leakage before you have to replace it. Working voltage of a capacitor. Is this a Q&A question?
I don't know. I did not this week's, but the following week.
Yeah?
And then all these actually kind of went pretty well with it.
Uh-oh, last week's?
No, next week's.
Because we talk a lot about condensers next week.
Yeah.
All right, working voltage of a capacitor. I do believe this is some sort of test question. Is it a Q&A?
I think if it's one thing, it'd be a-
Yep. Is the highest voltage,
It's a yes or no question.
is the highest voltage that can steadily be applied to a capacitor. Can steadily be applied to a capacitor without the dielectric breaking down. Hot?
Yeah. You break the AC?
I hope not. Let's see. It's dependent on the type and thickness of the dielectric. A working voltage should be 50% higher than the highest voltage applied. So if I had a 120 volt VAC, volts AC system, what should the working voltage of the capacitor be? 180. What do you get? So that's 120 times 150%, which is also the same as 1.5, equals 180 is my voltage. We doing all right there, Justin? All right, capacitor in a DC circuit. Capacitor in a DC circuit. Now, I talked a little bit about this yesterday. The symbol for a capacitor is two plates going like that. And if I look at it in a DC circuit, what does that look like? It's an open. So a DC, and really that's what this little thing I have right here is. It's a giant capacitor. Is it an AC or DC circuit? It's a DC circuit. And so when I connect it, which doesn't convey well on audio, but when I connect it, do I have a complete circuit?
Yes.
So yes and no.
Yes and no. Do I have a complete circuit?
Kevin, I can't speak yet.
I know. I've already charged it apparently. Discharge. All right. Back to charge. Do I have a complete circuit? For 5 time constants I do, and then it fills up, and so now it's just what?
Now it's open.
Now it's just an open circuit. So capacitor in series is going to look like an open.
Kevin, before we move on,
Yeah.
it says working voltage should be 50% higher, and then you have 150 down here.
It's plus 50%. So 50% more than. So that's 150%. Is it easier if I just say 150%?
Yeah.
Okay.
Surely.
I'll make that note so I keep doing it. But doesn't the Q&A say 50%?
I think it does.
So your Q&A says 50% is the right answer.
50% would be like
Well, that would make sense if your highest voltage is 120 and you add 50% to it.
that's 50% of 120 is 60. 60 plus 120 is.
Well, you just have to be careful how you do the math, because if you did 120, some people have trouble with math, that's okay. 120 times 50% equals, so I said, oh, it must be 50% more. So they do 150 times 50, then you're going to say, oh, then it must be 60 volts, right? And that's wrong. So you have to multiply it. Well, okay, you can do this. 120 times 50% is 60, but then you better add it to the 120 that you already have for 180. Do you follow that?
Yeah, I follow that better.
Okay.
I just didn't know how you're getting 150. So.
Okay, so the math is 150. You just do times 150, you get 180. Everybody follow that? Okay, because I kind of did that like really quick. Justin had a good point. Back to capacitor. Thank you for bringing that up. A capacitor in series. Remember, this is DC. Will act as an open. Oops. Act, ACT, as an open. Capacitor will simply just charge up and electricity stops flowing. Should I write that? It's a lot to write.
Is that how they make blinking lights work, or is that something totally
That's totally different. They hire a little monkey just to flip a switch up and down. And they give him a metronome. Tick, tick, tick. So it does it, it doesn't. Then we got Dennis back there. I swear, man, every third blink's a little lower. Slower. What movie's that from?
Freaking hippie.
It's from Cars.
Yeah.
You know, when you go to, my son told me actually when you go to Disneyland and you go to Cars Land, the third blink is different because it's really hard to see, but it is. Capacitor, off the track, will charge up.
Supposed to be like number 1, like that's the next no?
Yes.
Okay.
So F1, I1. Unless it makes sense to you to put 1 the capacitor. The capacitor will charge up and, what am I saying? And what? Current will stop. Current will stop flowing. There. Because I feel bad if I say it and then I don't write it. What about a capacitor in parallel? And again, we're talking about DC again. Still talking about DC. Capacitor in parallel will act as a reservoir.
Parallel DC.
Uh-huh. So it would look something like this. So I can put a load. And I could just put a capacitor in parallel. That's in parallel, right? Okay, so what happens in a situation like this is we could change this to maybe a light bulb. Add a light bulb in there. Here's a light bulb. And so what would happen is as I flick on the light bulbs are one of those things where, as we've learned, has a higher current draw when it's first turned on until the bulb starts going. So there would be a bigger draw on the battery until I got going. And so this capacitor would feed in extra electrons to compensate for the sudden need. And so that would then smooth out or act as kind of a filter or reservoir. Now another thing that capacitors could be used for, I'm just making simple stuff here, is maybe a switch that goes to something that has a high current draw. And the problem with that is, as the switch is closed, everything's fine and well. That current flowing through, and this could be kind of a heavy load, let's say, and maybe it's a big light bulb, and so current is flowing through and that's all fine. If you have enough voltage, usually not enough from a battery, but some things like magnetos that have very high voltages, as you open up the switch, what happens when the switch is just barely opening, it'll arc across. Right? It arcs across and it starts burning the switch out. So you can put a filter like this in. So what happens is when the switch is closed, then all of the current is flowing around through the circuit, not through the capacitor. And then as I start to open the switch, again, I'll personify again the electrons. Electrons are flowing. We're like, hey, wait a minute. It's getting hard to go this way because there's now a gap and we got to jump across it. And he tells all his friends over here, he's like, dude, there's a shortcut with absolutely no resistance over here. So instead of wanting to jump across this switch, they all turn around really quick and they run down this way because they think it's a path back to the battery because it appears that way. And they all start piling up on this plate until the plate gets full. And they realize at that point, we shouldn't have went this way. It was a dead end. You lied. So they all turn around to go back up the switch, but by then the switch is really open too far for anybody to get across, and now they're stuck here.
So there is no arc.
So there's no arc. You tricked all the electrons to not arc and go the easy way.
So, if the capacitor is already charged, right, then what will happen?
It's
Right
not.
Now it's like nothing.
It won't be.
Has it never charged?
Well, it's not that it doesn't have a charge. It's just not charged as much. So it's going to have, I would say, probably an equal charge.
No, like.
But then when you,
Sorry, go ahead.
I want to say it like this. Imagine if it is that the potential is all the same through this branch. So whatever voltage is, whatever voltage you measure across here, you measure across here, you measure across here. So the voltage is all equal, which is not to say that this couldn't be charged up more. So open it up, it'll charge more. If you want to look at it that way. Yeah.
So, how long? Okay, so capacitor.
5 time constants.
No, I've heard that. No.
You asked how long.
I've heard capacitors that they hold their charge for a very long time, like in years sometimes.
Yeah, I don't know about that. I mean, where's it going to go? Small ones leak down fast.
Well, if it's already charged and you reconnect the circuit, for
Uh-huh.
example, for like the light bulb,
Mm-hmm.
would it just be an open instantly?
I don't know.
Okay.
It depends. Okay, it depends on the size of the capacitor, the dielectric material, and what it's used for, and how the quality. I've talked to electricians who said that large capacitors, very large capacitors,
Yeah.
can get charged up by having fluorescent lights in the same room with them.
Okay.
So, yes, in that case, you take a capacitor, put it in a room with fluorescent light, it'll stay charged for years because it's getting charged from the fluorescent lights, which
Well-
sounds crazy, but I believe the guy.
I mean, the example that I've heard is electricians working on TVs.
Yeah, I was thinking of that one. Yeah, I remember as a kid, my dad getting the snot zapped out of him from the capacitor.
Yeah.
So,
Yeah.
I'm going to say I don't know about staying charged for years, but if I saw a capacitor like that, I'd be deathly afraid. One of the things that you're going to be talking with Phil about is capacitance discharge ignition systems and the potential to get knocked on your butt. You guys have had that class.
Oh, yeah.
So what's the deal with those? I don't know. Some other semester.
Hey, 1 week at a time,
Yeah,
Kevin.
you have to discharge
we
it,
can have
make sure it's locked out, no one turns it on while you're working on it. It says igniter box, right?
Yeah. Why?
Because it'll kill you.
Yeah. So these anyway, so a capacitor in parallel will act as a reservoir. We'll hit that again when we talk about magnetos, because that's where a magneto is going to use one in parallel. Let's see, where are we at? It can be used as a reservoir. I have some points here. I'll make them black. Points can be used to smooth out choppy DC. So if it's not a nice DC wave and it's
That's a Q&A.
got some waveforms that aren't quite nice. I hope that's not anybody's heart rate. The capacitor then could fill up and absorb absorb some spikes and fill in some low spots. So when you're done, it might look a little bit better. All right, smooth out choppy DC. Can be used to protect points. Points is another name for a switch. That would be a point in the magneto. Points, which is a switch in a magneto.
Is it the same thing with like a distributor cap as well?
It's exactly the same.
Huh.
Exactly.
I always wondered why that's in there.
Yep, it's protecting the points when it opens. So there's zero difference between my scenario here and a magneto and distributor. Supply a current for a short time. How long? About 5 time constants. All right, if a capacitor is connected in series, if a capacitor is connected in series and voltage is applied, current will flow at a maximum until the capacitor is charged. Current will flow at a max until capacitor is charged. And that's an important point. It's charged with where we're going, because you have to realize that when the capacitor is in a circuit, what the electrons see is a wide open 6-lane highway with nobody on it. There is no resistance to the capacitor. And with all that surface area of the plate, those electrons just run away. So with the slightest amount of voltage, you get maximum current. So just like with this battery, if I took somebody else's ammeter and I go across these terminals, how much amperage do I get? All of it, right? Even though there's really not a lot of voltage, I get this massive amount of current. Anybody care to guess how much current I get out of this battery? You should know.
300 amps.
somewhere around 300. Pulse hot cranking amps is 460. Which should be a clue to those of you who tell me on your project that you just got 3,000 amps of current draw. Probably not. Okay, so you're going very little very little voltage in a circuit with capacitors will have a large amount of current flow. Which is to say, if I look at something AC, and there's my AC sine wave, and we'll start right here at 0. I have barely any voltage going right there. When is my current going to be at the maximum? Like right away. It starts flowing right away. So I give you a choice. Is current going to start flowing most when it reaches voltage maximum peak? Or is it going to be peaking out right away and then falling off as it charges? And then when it changes, it's going to peak out right away. So that is to say that the current leads the voltage, and that's why. It takes very little voltage to make the current flow. So very little current, you have max, very little voltage. Very little voltage, you have max current flow in a capacitive circuit. It's the opposite is an inductor. An inductor, as soon as you have voltage starting to go, what does the inductor do? Don't come this way. I don't want you. Right? And with a capacitor, the second you get voltage, amperage is, come on, maximum. Boom, everybody, go. Right? You guys awake? A little bit. Am I boring you? We just go right to the test. Let me see. And of course, let's see. What happens when the capacitor is charged? At the point the capacitor is charged, no current flows. No current flows, and the voltage of the capacitor, well, I'll just leave it at that. No current flows. I don't want to make confusing stuff.
Okay.
Yeah.
If that's the case with the wave, so the capacitor stores power, not amp power?
What is power?
Well, I mean, because amp power is just the capacity.
Okay.
Not power, which is watts. Because
Is it?
it isn't conceptual. Like, I mean, like it isn't
Is this going to be relevant to this
Yes,
discussion
it is.
for the class?
Probably. Because if it's delaying or if it's leading the voltage,
Yes.
then why is it when the voltage goes up, why would the amps go down?
At what point? The voltage is going up right here, right? And is the amps going down right here?
No,
No.
but
But when
if it
it's
leads,
still voltage still goes up, but the amperage goes down.
I don't know.
I don't think he does either.
I'm afraid. Number one, I honestly I don't understand the question.
So
And number two, I'm worried that the answer you're looking for is again beyond my knowledge
No,
to a point where it gets into dealing with how to make a capacitor. And I just don't know these
it's
things.
not that. It's,
Okay.
I think it's a lot
Do
simpler than that.
they peak the same?
Because
Are you trying to make sense of this drawing?
Yeah, that's the thing.
not really.
Okay, good, because it's just kind of drawn crudely to illustrate a point.
If it leads the amperage leads.
It does, not if, it does.
It does. It does. When it does,
Yes,
that means that as the voltage gets higher,
yes.
the amperage goes down.
Doesn't necessarily go down.
It decreases.
It stops, the amps stop flowing in a capacitor circuit. Why does it stop flowing? It's full. It's got nowhere to go.
I'm talking about the AC circuit.
Hmm. It's full.
Oh, so it's just
So if
okay.
it's DC, so the voltage goes up and the current goes down.
Yeah, so obviously
Constant.
DC would be voltage would go up, and voltage stays that way, and then amperage would go very high and then back down to nothing.
Uh-huh. Uh-huh.
Okay. I'm just going to tell you these notes just because I threw them out here. So I wrote, at the point the capacitor, I'm going to hate myself. No current flows and the voltage of the, capacitor actually opposes the battery. The negative, no, I'm not going to do it. This will open up a can of worms that I just don't even want to try and get back into the jar. All right, it's not important for where you're going with this.
I'm not gonna write it down, but it's gonna be on the test.
It is not. All right, time constants.
Okay.
Time constants. Well, because you got to know, just like an inductor. Just like an inductor, it takes time. It takes
Pick that up from the name.
time to charge and discharge. And let's just cut to the chase. It takes 5 time constants. And I've already told you what a time constant is. I've already told you how it's figured out.
63.63.
And we don't need to do it anymore. So just know, it takes a while. How long does it take? 5 time constants. How long is a time constant? How long is it?
I don't know.
I don't know, it depends. It's the right answer. I don't know, it depends. What does it depend on? Resistance and capacitance. All right, just yeah, I could see. I was helping you out there. All right, so that was really, I've talked mostly about capacitance in a DC circuit. I've thrown in some AC stuff, but now let's talk about in AC. Capacitance in AC circuits. All right, so it's important to note, if I have a capacitor in series in a DC circuit, then the series DC circuit is going to see a capacitor as a what? Opposite of a short, an open. So if I take that theory and I put a capacitor in series in an AC circuit, is it still an open?
No.
It is not. And I think I talked about that yesterday, because what happens is it's just kind of tricked into thinking there's something there. So all the electrons are going to start flowing this way, and they're going to build up on this plate. And about the time this plate starts to get full, this is going to stop and it's going to go back the other way. So now all the electrons are going to come off of here and flow this way and start building up on this plate. Then it's going to turn around and go that way, and they're all going to come off of this plate and flow around and flow this plate. So as far as this circuit goes, if I put a light bulb in here, you're not going to know the difference. Light bulb's just going to go.
Does that mean that the capacitor must have an initial charge?
Doesn't need it has to have an initial charge at all. It could be completely dead. When you turn on the power, what's it going to do? It's going to charge itself up. So because AC is constantly changing, it is constantly changing direction, a capacitor will charge and discharge constantly, making it appear as though current flows through it, when in fact it is not true. A capacitor will charge and discharge making it appear that current flows through. When in fact it doesn't. Does not. But it looks like it does. So you can put a capacitor in series with AC and it's going to work just fine. Let's see. We've already talked about this. When voltage applied, maximum current flows instantly, immediately. This is because the capacitor plate easily takes a charge, which is a flow of electrons. Max current happens as soon as the voltage moves from 0. So right away, I already wrote that. In an AC waveform, max current is at 0 degrees. As an electron builds up on the plate, the capacitor opposes additional current flow. There is zero current flow and the voltage is maximum. Do I need to write all that? Okay, good. Therefore, current leads voltage by 90 degrees. So current leads the voltage, which is the Iceman. Ice. Current before voltage. And then when the current changes directions, then all of the charge starts flowing the other way. Christian, help me out with this.
Frequency.
Thank you.
What did you just say?
Frequency.
The amount of current the amount of current that a capacitor allows to flow is dependent on the capacitance and frequency. More capacitance equals more flow. Higher frequency, more frequency. Yeah, we'll go higher. That's a better term. Higher frequency equals more flow. All right, how do we figure capacitance in a circuit?
Assuming you're gonna get the formula.
Assuming that total capacitance in a circuit it's kind of a bigger I. This little I is the opposite of resistors in a DC circuit, or just opposite of resistors and inductors, actually. So that is to say, in parallel, the equation is C total, which is capacitance total, equals C1, what? Plus C2 plus C3. This is the formula for resistors in series. So what happens, but in capacitors, it's the opposite. And in series, it is C total equals 1 over plus 1 over C2 plus 1 over C3, and then all that with 1 over. And that probably doesn't make sense right off the get-go why that would be. And the reason is because I need to draw it, but I can't. So I'll just tell you about it, and then I'll draw it. Well, I'll draw it over here in the corner. So if I have plates in parallel, they simply just add up. So you can see that it comes to here, and you have that plate, comes over to here, and you have that much plate, come over here and have that much plate, and you can kind of imagine that you could just squish them all together, and it would just look like this. Right? And so you just add it up. So in parallel, it's easy. You just add them up, and here's the bottom of the plates, and they just kind of connect together. And so all of the surface area is easily just added together. But when you take and you put, so that's why in parallel, it just becomes plus, plus, plus. But when you put them in series, why does it become all goofball? Oops, because I'm drawing a goofball, that's why. So if I put a bunch of them in series, let's think about. I keep doing that.
What's your deal, Kevin?
I don't know what I'm doing. All right, I'm done. All right, so when I put them this way, let's think about what the electrons are doing. All right, so an electron, they're flowing this way. These are my electrons, and they're going to build up on this plate. This is going to push the ones from here, because like charges repel, this way, and they're going to build up on this one, but not as many. And then they're going to build up on this, but they're over here, and it's going to push these across, but not as many, so it's diminishing. And then these are going to then push that way. So you don't add them up, it's actually diminishing. These electrons that are kind of stuck between here and here, they sort of live there. And that's why it's a lot less than adding them. You can't add them together. I don't know if that was the best explanation, but maybe visually I hope you can see it. Yeah.
It's like like a mountain valley, right? There'd be smaller ones on the sides and then a big one in the middle.
You're not right.
So it's the same rule applies for the total amount is going to be less than the smaller.
What's that? The mountain's what? Is the
The
mountain?
total amount will be smaller than the smallest.
Yes, the total amount is going to be smaller than the smallest one. So, all right, now I'm going to move this over.
I did not know.
What?
That's crazy.
What did I write? The reasoning is that when capacitors are in series, the total capacitance is less because the center two plates do not contribute to capacitance. In a parallel, the total plate area is added together because each capacitor acts independently. So total capacitance is the amount of total capacitance is the amount of capacitance that does not. But that does not tell us the actual opposition to current flow. Ooh, okay, if I say that slowly enough, it makes sense. So do you want me to write that bit about capacitors in series and parallel? Because I gave you the formula. You got that?
Yeah.
Okay. And it tells us capacitance, but it doesn't tell us the opposition to current flow. There is an opposition to current flow because especially when it's all charged up, there's an opposition, right? Which now acts like resistance, but a lot of it. But capacitance doesn't give us any indication of that. I can't just equate it and say, well, if it's 1 farad, that's going to be something like 1,000 ohms. Well, it doesn't work that way. So we have to figure out total capacitance capacitance in a circuit. So which we just did. So then we have to figure out what is the resistance equivalent. Any guesses on this one?
Capacitive react.
Oh my gosh, there's a guy who was awake or something. I don't know what happened. Capacitive reactance.
It's all the same words.
Well, yeah. All right, and this is the opposition of current flow. Opposition to current flow. In a capacitive circuit, or the opposition that the capacitors are providing in a circuit that has capacitors or resistors, inductors. I feel like this is something we've talked about before. Measured in, guess? Ohms. Guys are so smart. But due to phase shift is not considered resistance. Have you wrote that before?
Yes.
All right. I just cut and paste right here. Due to phase shift is not considered resistance. It is represented as what's my symbol going to be? X of C. What's X of L? Inductive reactance. All right, so it's kind of following the same thing. So we have X of C. 3. Capacitive reactance, now I can just say X of C, is inversely proportional to the capacitance and what, Christian?
Frequency.
The frequency.
Thank God you're here.
Hey, when you're right, you're right. Am I right?
Right.
Right.
Left.
The formula
It's the first time he's been right in a while. Just
that you want to put on your formula sheet is that x of c equals, hey, what was the formula for inductors? 2 pi f
L.
L, but I'm just going to put a c. That would be too easy. But remember, it's a little bit different, so it's 1 over. So it's 2 pi fc, but it's the inverse, or divided by 1. 1 divided by. All right. So x of c equals capacitive reactance. Measured in ohms, or Lululemons. Where F is what? Frequency, which is hertz. And C is capacitance in what? Farads. And that is a perfect spot to take a break.